restoration activities, such as governments or large companies. By the way, we just started recording the meeting, which I forgot, so thank you for that. You must have some notification already. So the question for these stakeholders who can really mobilize the resource and the effort to be achieving all these ambitious targets is, how do we assess a large-scale landscape restoration potential? And by large scale, we're talking about national or biome-specific geographical coverage. We're asking the question: are the current targets really realistically ambitious? So is it we don't want to have a target that is, not at all realistic, so it is impossible to achieve, but we also don't want a target that could have been achieved by yesterday, basically. And finally, how do we formulate operational restoration policies? What are the elements of a policy that needs to be there to ensure that we actually have the impact delivered? So to address this issue, our project is doing things on three main areas. First of all is the crux of what we are talking today, which is the mapping component, where to restore, what area to restore. And later on, we're going to go through a lot of details and some examples on how we are technically addressing technical challenges within this element. The second question that we are addressing in the project as well is the option. So what kind of restoration intervention we can do, what kind of trees we can plant, for example. And finally, are the restoration options feasible? So not only from a perspective of how much these trees can grow, which by the way, of course, varies depending on the location and also on the different stages of the lifetime of the trees themselves, but how do they compete with other land use activities within that landscape, and therefore feasible and sustainable in the long term. Obviously, these three elements, they are intertwined. So when we talk about a certain area, then the options that we have are very specific, of course, to this area. And it has to be compared against competing land usage in that area as well. So these three things are intertwined, and here we are focusing on describing what we address in the first part of our project, which is identification of areas to restore. And just to explain a little bit, the complexity here is that we have, Google Earth Engine is probably one of the facilitators of so many research, so many studies that have generated a lot of global assessment of areas restoration potential. They are under different names, areas, global maps, global atlas of degradation, maps of restoration opportunities, many names. But there is a huge spatial discrepancy between the different products, as you can see here. And the discrepancy is not only in terms of the total amount, but also in the spatial distribution. So there is a lot of uncertainty. Talking about Indonesia, very specifically, we have similar situation when there is a lot of uncertainty, and some of these uncertainties are related to the different definitions. So you have different definitions coming from Ministry of Agriculture, from Ministry of Forestry, from the land agency, and they all point to the same thing, which is a better map, a better understanding of areas in which we can conduct restoration activities. So that is what we are trying to do in our project. We are trying to identify areas not only from its biophysical state, but also from its socio-ecological, from its social and legal aspects. So including land use histories, including the current land use activities, including the legal designation of these land use. And at the crux of this is, of course, the land cover map, which we will then explain in more details on the technical side. This approach will generate what we refer to as the map of restoration potential. So initially, I mentioned a lot of about degradation, and you're probably aware that the last two slides, I'm not mentioning degradation anymore because our approach is no longer about degradation, but it's really about where restoration can be conducted. So it's not about identifying which area has been degraded, but identifying areas where we can conduct nature-based interventions to enhance carbon stock, biodiversity, and other ecosystem services. So by this, we try to eliminate the potential problem coming from uncertainties and therefore the requirement of, so to say, reconciling the different understandings, definitions of degradation. In doing this, we are generating a product, a platform, so to say, multiple products. So a platform, and then a lot of products coming from this platform. So the platform itself is called Urundata. So for Indonesian language speakers, Urundata means, as you know, literally donating data. So it's a platform where the crowd can contribute their knowledge on restoration-related issues. We are specifically doing 3 elements here. We're doing crowdsourcing of reference data to map the restoration potential, crowdsourcing, reaching out to the general public, as you can see here, but also to some extent to the remote sensing community, which I think some of which are even present in this meetup. The platform will then be used to disseminate the results from our participatory mapping, including the algorithms, the codes that are used, and the participatory mapping revolves around mining open source or publicly available satellite data. And finally, of course, we are doing dissemination of the results, not only in the maps, but also the findings and the insights coming from that. So yeah, I guess that's all as an introduction of the overall project, the bigger picture beyond the mapping activity that we are doing. And hopefully that can spark some idea and give you a little bit background of some of the more technical stuff that is going to follow. I guess the next we're going to have Hadi and Olga do some live demo of the specific approach that were used in generating the land cover maps for mapping restoration potential. With that, I switch to Hadi as the next speaker. Please, Hadi.
Yes, thank you, Pic. Can you see my screen now with the slides?
Yes.
Perfect.
Yeah, I can see the screen perfectly.
Excellent. Yeah, thank you, Pic, for the introduction of the overall approach of the Restore Plus project. And now, in the next 10 minutes or so, I'd like to present the theoretical overview of the technical implementations of the stream of work, which is to produce this land cover map at national scale in Indonesia, utilizing Google Earth Engine, as well as crowdsource reference data collection approaches. So my name is Hadi. I'm a research scholar here, remote sensing specialist at IIASA. So the requirements for Restore Plus have been defined together with the country partners, as Ping mentioned just now. We at IIASA, we collaborate closely with ICRAF, World Resource Institute, and WWF, World Wide Fund in Indonesia. And from the project requirements, the requirements for the land cover as a product is that it has to cover the whole country at national scale. The spatial resolution being 100 meters, compatible with the existing maps that we have. And we are producing the map for the year 2018. And in addition to delivering the map as a product, we are also focusing on the design of the system itself, capitalizing on Google Earth Engine, as well as informed by the many similar initiatives, large-scale land cover mapping initiatives that have been demonstrated all around the world, such as by the Severe Group, where they have demonstrated the use of Google Earth Engine in the Mekong region of Southeast Asia, but also in many other regions of the world. The Map Biomass initiative in Brazil, the Copernicus Global Land Cover Layers done by the team in Europe, as well as the other approaches as well in the other countries. So we have a lot of now demonstrated workflow that we can adopt, like we can adopt the bits and pieces from the different methodology that has been implemented, that has been made possible by Google Earth Engine. For the thematic resolutions, here is the critical part in the implementation of Restore Plus. As we know that the land cover classes that we should define, it should really be relevant to the purpose of the work, of how the map will be used. And in this case, the map will be used to assess the potential restoration areas. And at the same time, it has to also be relevant to the country of implementation, Indonesia in this case. in the sense that it has to also follow the existing land cover typology, the national standard that we have in Indonesia. So the design of the land cover classification scheme, it consists of mainly 4 broad classes here: forest, tree-based system, non-tree-based system, and the non-vegetation class. And importantly here that the forest classes have to be further detailed into the dryland or wetland or swamp mangrove forest. And for each category, we need to have the undisturbed and the locked over class. Under the tree-based system, we are required to map separately the agroforestry, plantation forest, rubber monoculture, oil palm monoculture, and other monoculture. And on the right-hand side, I showed 2 sort of the locally defined definitions of these 2 example land cover classes. But in the interest of time, I will not describe them all, but we will distribute later this slide, and you can find like all the definitions, the country relevant definitions of the different land cover classes that have been defined in this project, Resourcebox. And next is I would like to give you an overview of exactly concretely how we have implemented Google Earth Engine in the whole end-to-end pipeline in producing this national scale land cover map, which consists of preparing the input data, so the satellite data, the Earth observation data, and how we then can, what we call as feature engineering, we can derive additional predictors or covariates for the land cover classification task. And of course, it's a machine learning supervised classification, and therefore we require to have the training data, the labels, and all these ingredients are integrated in our engine. And then we check the results and we improve the results iteratively, continuously. And so this is really the unprecedented capability that has been made possible by Google Earth Engine, where we could relatively quickly iterate this process, focusing on the different components of the pipeline. So just to show in some more details of the ingredients here. So we start with the input data, the publicly available Earth observation data, so the optical data from Landsat, as well as the SAR, the synthetic aperture radar data from ALOS Pulsar and Sentinel-1. We created then this national scale annual composite from this Earth observation data, applying the necessary pre-processing steps, such as cloud removal, topographic corrections, and so on and so forth. And from this original spectral measurements, we could then derive the features, spectral features, the spatial textural features, as well as the temporal features. So the spectral temporal signatures all together derived from these original measurements. And all these steps can be implemented in Earth Engine. And having the input data, the predictors, we then require the training data. And for the training data, we benefit from the available reference map that covers the land cover classes that I've just shown just now. And therefore, we can place many points, training pixels, training samples, having them balanced for the different classification scenarios that we have, as well as the different classification regions. Where we train the machine learning model and we apply the model separately to account for the different characteristics of the land. Having all the ingredients, then we can then fit them into the machine learning algorithm, random forest in this case. We then do the feature selection. We do the hyperparameter tuning to then produce the result from the machine learning. And importantly here, what we found to be able to account for the complexity of the classification scenarios here, instead of doing a single multi-class classification at one step, we divide the problem into a series of binary classifications, producing from each case the predicted probability. On top of the predicted probability from the machine learning algorithm, we found that it's very necessary, it's very critical to add additional expert rules on top of the predicted probability from the machine learning algorithm. And of course, after that, we need to do some post-processing of the map to ensure the temporal consistency, removing salt and pepper noise, implementing accuracy assessment following good practices, statistically defensible accuracy assessment processes as well, and continuously then we can refine this pipeline, focusing on the different ingredients in the pipeline. So this boils down to some of the aspects or like components here that I show. Reference data for training the machine learning model, reference data to do the accuracy assessment, as well as improving the input satellite image-based predictors, and so on and so forth. And importantly here that in the project, we have implemented the crowdsourcing approach to some of these aspects that I will show in the next few slides in the demo as well. So two ways the crowdsourcing approach have been implemented in the project is that firstly in collecting the reference data for training the machine learning model, in which case we employ this public crowdsourcing approach where we crowdsource the task of verifying the training samples that we have derived from the existing reference map, given the fact that of course there will be errors in those, there will be like noise in the labels from the reference map. And here we deploy the public crowdsourcing approach using a mobile applications, and this then results in high quality training data. And the classes that we can crowdsource the task to the public consists of those following classes as shown in the slide. The other crowdsourcing implementation that we have deployed in the project is in collecting the accuracy assessment samples, in which case we have to rely on a more expert crowd using a more expert tools as well, which is GeoeKey that has been developed in-house here at IIASA. And with that, I think I would continue with demoing some of the tools that we have developed using Engine apps to collect data in this crowdsourcing approach.
Hey, Hadi.
Yes.
Sorry, just to very quickly give some feedback to some of the question that has been put in already into the chat. I guess we can, I think these are clarification questions, so we can address it quickly. So I've listed 3 questions. First from Trisha, which is, I'll just read it out. When defining monoculture for the mapping bit, what is 100%? For example, in the definition of rubber monocultures, what is 100% mean? 100% of a pixel or canopy cover? So that's the first one. You want to quickly respond to that?
Yes, so the definitions come from our local experts. And in this case, it's typically considered to be sort of more than half of the area. And of course, then in interpreting the reference data, the unit, a pixel then where the dominance, like more than half of the pixel consists of that particular commodity, then it would be classified as a rubber monoculture following the definitions by the local experts.
Next question, how do you interpret the mangrove systems? I think I'll just limit this to clarification question. So please just quickly address this, Hadi.
Yeah, so I think the best thing is that later on, I would advise then our participants to go through the slides that we will distribute, where we lay out all the definitions that have been defined for the different land cover classes, if that's fine.
Perfect. Okay, so I guess that will be the same. There's a question about more details of the ancillary data and preliminary result of the accuracy. Okay, just quickly, pixel size is 100 meters?
Correct, correct. At this,
okay.
Yeah.
Great. Okay, perfect. So I think we've addressed most of the questions, and others we can continue in the discussion or later on. So please, Hadi.
Yeah, thank you, Peng, for that. And I think this is actually great, because indeed the classes, the land cover classes that have been defined is way, it is of greater details than existing, let's say, implementations at regional or global scale, where in some of the products, a lot of the classes are simply grouped as a forest class. But to be relevant for the country implementations, the country level policies, those level of details are required, and therefore understanding the exact definitions relevant to the stakeholders there is indeed like one of the critical components of our project here. Right, so I think I would probably take the next 10 minutes or so now to just give a quick sneak peek of some of the tools that we will share as well, utilizing Engine apps, particularly in the task of collecting high quality reference data for training the machine learning model here. So here's an app that are publicly available. And the idea of the app is that it first of all, like introduce to our experts in Indonesia how machine learning is implemented to produce an automated land cover map, and gives them also the possibility to quickly test for different geographical areas in the country, in Indonesia, for different sets of classes that may be or may exactly have the same definitions or may not have exactly the same definitions as, for example, what we have in Plus, and quickly really see the promise of doing so using automated machine learning methodology. So what we have here is that this app has been added with the layers of the Landsat composite for 2018 in different visualization combinations, as well as the Sentinel-1 backscatter visualization combinations. And here, just an example, if then the expert are interested in mapping this area, and he is or she is particularly interested in the classes of this rubber monoculture and oil palm, as well as the others, he can he or she can start with that. So I can put my name here, and then I can put the classes that is of interest here. So for example, I'll put rubber, oil palm, and others. Yeah. And then I can click this create geometry layers. And what it does then, it will add these geometry layers to the drawing tools. That was like a recent feature, like last year also, if I'm not mistaken. And then the operator can start collecting training data by drawing polygons on top of this high resolution base map by Google, as well as any other prepared layers that can be used to interpret the different land cover classes. So if I start with the rubber class, and then I will collect a polygon in this case, and I could draw polygon for rubber here, and then I can collect as well for oil palm. So I draw also a polygon for training data for polygon for the oil palm monoculture class, and I need also the rest, which is not oil palm and not rubber. So I will draw here in this settlement here, and probably also here, just as an example. And after that, I have the training data. Then I can go to the next step, which is to look at the predictors, the covariates that I can use. And then, for example, here I just use everything that has been prepared here. And then we can run the classifications for relatively small areas on the fly, like so. If I click this button to run classifications, then the selected classes will appear, and the classified map running in the background on the fly using random forest machine learning algorithm will also appear like so. And the benefit of this approach is that then the machine learning result can guide really the operators, the human operators experts, in targeting the areas where we need more training data, right? So for example, if he or she would like to check the transferability of this training data to different areas, he could go to different areas and run the classifications within the extent what is shown on the map here. So I can run again here the classifications, and using the training pixels extracted from those polygons drawn earlier, then he or she could check whether he or she needs a really additional training data for those classes in this area, or actually the transferability is good enough and therefore it's sufficient. So this sort of human in the loop process of collecting data aided by machine learning is going to improve towards the efficiency of collecting training data. And to download the training data that has been collected, then the operator can click this button, which then will download those polygons with the labels as a GeoJSON file. There. And as a crowdsourcing approach here, the idea is as well to collaboratively then collect this training data together. And so if we can imagine having a vision where different persons contributing this different training data for different classes, and we have a repository consisting of this training data for the different areas, that would be then for the benefit of the wider land cover mapping community, in this case in Indonesia, for example. So I think this is just a quick demonstration of how we have developed this tool on our engine to collect training data aided by machine learning. And for the next demo, I would also show this app that we have also developed in the Resourcebox project. And the purpose here is that to give an overview to the local experts of the process of creating the Landsat composites. And importantly here that based on the feedbacks that we have received from the local experts, typically we need different compositing criteria, different cloud masking procedures, possibly different periods of the compositing within a year to represent the different land cover classes in different geographical areas. And so this is a quick way for the local experts here. For example, here I can define the starting date and the end date of the images here from Landsat that I would like to collect here. And I could choose what sensor do I want to use. Do I need to combine different Landsat sensors to produce as little as possible, let's say, missing of observations, or it's enough to use one sensor, right? So I can use all, for example. Then I can choose whether I want to pre-filter the scenes, the satellite images based on the scene level cloud cover there. So here I use all the available scenes regardless of the cloud cover. Then I can implement the cloud and shadow masking algorithm. And then if I just click here, this button to generate the composites, it will generate on the fly. Then these composites that have been defined based on these parameters here. And the idea is that the local experts can also visualize those composites and compare the different composites produced using different reducers. For example, is it a median reducer? Is it a percentile reducer here with 25th percentile being defined here? Or also the medoid reducers, or like the maximum intermediate reducer. So this different way of aggregating data to produce the best available pixel composite for the different areas can then be inspected, and collaboratively then the experts could then contribute this knowledge, like in different areas, what is really the optimal compositing methods. And this is critical not only for the process of visually interpreting those images, but this is also important that in the use of those images as inputs to the automated classification procedure. Yeah. So I think with this, I would end for now this showcase of the two tools now, one to collect training data interactively, and the other to sort of collect information about how can we best create the composite that is spatially variable and optimized for different areas. And with that, now I hand over to Olga, who will show another tool using Earth Engine to collect feedback for map we create. Again, that it can be used together with the local experts. Olga, please go. Please take.
Just a second, sharing my screen.
Just to interrupt while Olga is preparing, I just want to say that I'm looking into the questions. So there's quite a lot of technical questions. So don't worry, we will address them. We will address them as part of the next step discussion. So probably before discussing other things, we will first go back into the questions, and Hadi and Olga can provide some slightly more detailed answers to that. Please, Olga.
Hi, everyone. So my part of the demo, I'm going to show one of the tools that we developed as a part of the Restore Plus project. And as we all do, focusing on the mapping activities and collecting the training data, there's two parts of the pipeline that we all have. So it's basically collecting the training data for your classification according to your definitions. And then the second part of the workflow is actually validating your maps and collecting more validation data to collect and assess the quality of your products. So what I'm going to show here is the app that we built in order to collect the training data overlap with different land cover classes, land cover maps. And that code and application will be shared to everyone. So no worries, you don't need to be typing the links into the browser. So let me guide you through this application. So generally, the whole app consists of, the whole idea is that you can put on top of the map your land cover map together with your classes. And let's say this is intermediate step of your classification algorithm and you want to share it with your colleagues or other members of the team, and you want to get the first assessment of the map. And let's say, as an example, we took the Perennials land cover map, 100-meter resolution for the demo purposes. This app gives you a possibility to look on the map. You can change the transparency of the layer. And let's say you see that this class is not really well classified and you want to add some more training data covering this area of the map. So let's say you see it's not the forest cover here, but it's, let's put it as cultivated land management. So if you click on this label, it automatically chooses the layer where you would add the training data, and you can add a polygon on top of the layer. So if I press the Q button, it would disable and enable the land cover map. So let's say I'm zooming to another location and I see that there should be shrubs. So I can change to the shrub layer. So I have a look here, and let's say this would be my shrub layer. So I'm adding more polygons to the shrubs, and it's adding automatically to the geometry input. And let's say I have some layer with the settlement, and let's zoom it here, and let's say I want this to be classified in urban areas, although it's classified as that. So I choose the urban layer, and I'm adding one more polygon. While drawing that, I can be switching on and off land cover map, and I'm adding some more polygons here. So let me finish that polygon. So I draw a couple of polygons over here, and let's say this is also looks like urban area. So I add it over here. So what you have several polygons that you added to your map, which now you can download as a table, GeoJSON table. So if I click, it downloads into that. And it's all formatted in the way that can be readable with other geospatial data sets, and it contains all the information about the class and class name. So the general idea of this app, whenever you have intermediate step of your classification algorithm and your map, you can put your data into this app, and you can share it with your colleagues or other people that you want to ask to evaluate and correct some of the layers. Looking to the code, it's not that complicated, and this is the code that we will share also with you. Everything what it does, you can specify what is the most important. You can specify all these parts of the app. So you can specify the name that is displayed here and all the classes. So it can be just a couple of classes that you have, or you can have up to as many classes as will fit in the window. So everything what you need to do to make your own app is looking through the code. You need to specify your own classes, your own palette, and the image that can be in your personal assets uploaded to the Earth Engine or the output of the classification, and you specify the values of that map. And it's all what will automatically be part of the other steps of the script, which means the legend and the names layers are created all automatically over here. So this is, if you were a part of the app's workshop during the Earth Engine, you know how to write this code, and if not, you can just make use of the script that we have. Then we create all the geometry layers, and at the very end, every time if you click the download button, the latest version of the training data is uploaded. So I would not go line by line through the script layer, but it's something that will be shared, and you can have a look to what is actually over there. Yes, this is all what you need to know when you will be looking through the script, that you can change your image to your own image or any other image that you want to collect training data based on or validate. And you need to specify your own classes and your own palette for those classes that you want to be displayed on that map. And then the general tools, so you can either use the existing app that we will share the link to, or you can modify the script that we will be sharing on, and then go through the general steps of publishing your app according to the Google Earth Engine manuals, how to do that. And that's something that can be done within 5 to 10 minutes. If you haven't ever done that, that would be a nice exercise for you to try. Another maybe mentions, if you are publishing your maps and you're doing your classification, not yet in the using Earth Engine, but you're using it other sources, or like you're doing your classifications in Python or other tools, you can use also this app as a possibility to add the link, and it would you can create your own map visualization of your classified layer, and create it as a, just a second, you can create it as a permanent link and publish together with your paper, which would be displaying your classified layer on the map. Yes, that's it from my side. Yes, if you have any questions, please ask, and if not, we will share all links in the follow-up email.
Thanks, Olga. Yeah, I'm just gonna go through some of the questions. So first point, yeah, you can see Hadi's already sharing some of the links, but basically everything that we are demonstrating to you guys here will be made available. So either via email or from the Google Docs, so we will reach you for sharing the codes to these apps. So yeah, I guess directly into the questions that I've seen. There were some questions about how we interpret or how we deal with certain land covers. So Steya, I apologize for my terrible pronunciation of all your names. I do that in advance now. There's a question from Steya, how do we interpret mangrove? And I think there's another question from, I think this is Matthew Fagan, how we deal with jungle rubber. So I guess this will be best addressed by Hadi. You want to share something, Hadi?
Yeah,
I can at least start pointing out while you're sharing screen or something that jungle rubber, we deal with rubber monoculture as a separate class, and then we deal with agroforestry with multiple combinations of trees. Just briefly, please, Hadi.
Yeah, thank you, Ping. Maybe I would begin by saying that I may not be the best person to answer the questions regarding the definitions of the different land cover classes, but the process that I would try to maybe showcase a bit is that maybe I can show also a slide here, but it's fine maybe later. But basically, throughout the lifetime of the project, in the past 1 year or 1.5 years also, we have been conducting many expert workshops in Indonesia, and we invite experts from all around the country, from different organizations, the governmental organizations, as well as the civil society organizations, and we bring everybody to sit together to do visual interpretations using the GeoeKey tool supported by Engine. And in that exercise, we then try to learn really how the local experts make decisions to decide whether a certain area is a particular land cover class. And the idea is that we try to find the consistent rules there, for which that we could program those consistent rules into an automated algorithms. And importantly here, we see that that's exactly the challenge, because the experts they don't always agree, and this then requires us to really fine-tune the algorithms to represent the different areas, for example, where a certain land cover type can be defined differently considering the local contexts. So I think I can answer in that way that the process here, which is important, that the definitions have to be always communicated closely with the local experts from the different parties, I'd say. I hope that sufficiently answers the questions. But for more definitions, we can have it in the slide that we'll distribute after this. Yeah.
Thanks, Hadi. Next questions. I'll just summarizing the question. I think there were also some questions about the accuracy assessment. So what would be, if you can make a general comment of the state of the accuracy of the maps that's generated? And also there's a question about how to ensure the accuracy since there's a lot of data with different qualities being input into the work.
Yeah, thank you. So more details of the results will be reported in forthcoming publications. We are now at the stage of compiling the statistically robust accuracy assessment samples following good practices, as many of you may know already from Olofsson et al. Paper. And in general, what I could say is that when we have the local experts compare the resulting automated map with the existing available maps in the country that has similar detail of the classes or like comparable classes. The map has been found based on those accuracy assessment samples collected by the local experts. The accuracy is at least comparable or slightly better. It's not, I would say it's very, let's say high accuracy, like above 70% or so, but compared to the existing available maps that unfortunately may not always be accessible to the public, for example, the methodology has shown that the accuracy can be comparable, but more details will be found in the forthcoming publications.
Perfect. There are other questions, several from Trisha. By the way, hi Trisha, very good to see you here. So several questions. One, probably can you say something more about the ancillary data that was used in the automated mapping? Second question, why random forests was used particularly? And finally, who are contributing into in the crowdsourcing activities of the reference data?
May I suggest maybe Ping, you can answer the last question,
Yes.
the crowdsourcing approach? Yeah.
Of course, yeah. I can do that first. Actually, the crowdsourcing, we have two types of crowdsourcing. So we have the crowdsourcing that is targeting the general public. And this is mainly, we're targeting university students in all over Indonesia, actually. So we're doing this via a mobile application. You can type in just Urundata, which I'm typing into this chat now. And I apologize for my two K9 children. Yeah, it's using a mobile application, so we know who the users are, or we can identify who the users are. And these are university students. It's actually not that easy to get a lot of contributions, so we were pretty active and we worked pretty hard in engaging people to be contributing data actually. And then the second group of people are the workshop, are the experts, so to say. These are remote sensing experts, people who are used to remote sensing, people who are used to visual interpretation of land cover classes, not just from universities, but also from NGOs and government entities. So we hold workshops for them to be classifying, to be helping us with their knowledge in terms of what is the actual process of interpreting a certain location. Yeah, so I guess these are the two groups of people that we are targeting. So other questions, back to you, Hadi.
Yeah, thank you, Pink. So maybe I can answer the question about the machine learning part, the random forest algorithm. There are many reasons to implement random forest algorithm, and not, let's say, the deep learning algorithms that are most suitable for higher resolution sort of a map to be produced, such as the dynamic world map at 10 meters resolution that we saw being demoed yesterday. Since we have relatively coarse requirements, 100 meters resolution, the traditional or conventional machine learning algorithms are sufficient, especially considering the technical feasibility to implement it at national scale. And importantly here, I think based on our experience, we found that really the bottleneck, as has been also communicated by many other similar initiatives, is training data. So it's not the algorithm, but rather the training data. And the training data that can represent different classes, the details of the classification scheme that are required, it's really I would say the most fruitful way to improve the accuracy of the resulting maps in this case. So training data. Yeah, which is the reason why we also employ the crowdsourcing approach really to improve the quality of the training data and having more and more experts to arrive at, let's say, high confidence levels, interpretations, and therefore also high quality training data.
And in the topic of training data, Hadi, so there were also questions. First of all, what is the quantity required for the training data for sufficient quality of classification? And secondly, there's a question about how do we filter false input from the crowdsourced data?
Yeah, thank you. That's indeed I would say the crux, or the most important aspect of doing this crowdsourcing approach, we need to really implement quality filters, quality filtering to the data contributed by the crowd. We have adopted different methods to do this. One being, we also assess the performance of each contributor. We have some of the images labeled by experts, and this then are used to give a score to each contributor so that we know how well each contributor performs. And we also require that for each sample, we need to have at least 6 or 8 validations or interpretations by the crowd. And also we account for those individual user score in really determining the level of confidence we can have to the final label being generated. So indeed, that's a critical issue. On the questions about the number, I would say maybe also the allocations of the training samples. Maybe Olga, you could jump in a bit because this relates to also how we implement the classification scenarios into many binary scenarios for different regions and how the samples should be balanced. Maybe you could say a few words about that.
Once again, help me with the distribution of the training sample or about the quality of the data.
So more like the quantity of the training samples that are needed, and yeah, I guess in addition to quantity, also like the allocations, the balance of the samples for different classes as well in the machine learning implementations that you are also contributing a big part of.
Yeah, so that's a very difficult question because they're generating like there's 2 pathways to the training data. You can have smaller amount of the data that is like carefully created and curated, so you're very sure about the quality of the training sample, but you cannot collect much of that training data. And another part is generating the training data using existing layers and line cover maps while bringing them to the same definitions as you are trying to target and classify. So I would say we had partly mixed approach when we would be having our expert collected training data according to our definitions, which we would use to evaluate the layers from which we will be generating the training data, the bigger amounts of the training data. And we would stratify according to like into the different classes while from the best available maps. So let's say if we would have 10 different classes, we had more classes, but let's say we would focus on the water layer or urban layer. And for those classes, we would use the best available classified maps as the global water layer or the Facebook settlement layer, which has very good coverage, especially in the region that we are focusing on. And I think the biggest limitation is if you're using like global products and there can be many different land cover maps, they can be better in certain regions and worse in other regions. So that's something when you are focusing in your other like smaller area or region or like continent, you need to see which of those global products are better for your region. And that's how you decide which classes from which map you would sample based on the accuracy, based on your own evaluation. So I think we basically went through each of the classes and tried to take the best available global layers or local layers and generate the training data from those. Yeah, that's from my side.
Yeah,
and
yeah. Please, if you have something more to add.
No, about the crowdsourcing data. So because there were 2, like I would say like 3 different tools used. So what we were using, there were some internally built IIASA tools for quick classification, like the picture pile, Hadi was saying, and GeoeKey type of tool where you can specify the whole questionnaire for the experts. And that's where you can implement the quality assessment, and the quality assessment and quality check is something which is very important when you talk about the crowdsourced data, because you want to know how to filter the faulty data and or the wrongly classified labels. And that's what is easy to implement. And I just wanted to mention on the demo that I was showing, where you can put your map and you can collect additional polygons of training data. This is intended to be used to share with your colleagues that can help you to collect more training data in the areas or correct your map so you can use the input data. And also that can be used as if you publish your paper and you want to say that there would be always people saying that, oh, in this area, and I'm from here, this is not forest, this is plantations, and you miss this area. So if you publish your map together with the tool, saying that if there is an area that you think is wrong or can be improved or implemented, you can share also this map and ask people to send you back the areas that they think needed to be corrected. So you can also, for the version 2, 3, or next versions of your map, you can improve those areas or just understand which classifications were missed on your initial classification and improve on the next iteration of your algorithm.
Exactly. And I think I just would like to add the keyword here for training data optimization is really the geographical diversity, which is now recently increasingly recognized. It's not mere the quantity, but importantly, that's why like this process of having the machine learning always informing the humans to really see whether a certain area is homogeneous enough that a limited amount of training data is sufficient, and therefore the efforts could be targeted, focused on areas where it's different from those areas where training data have been collected, and therefore it requires more training data over there. So geographical diversity is something that is increasingly being recognized, especially considering like, for example, when we look at many globally available map products, when we zoom in different local areas, of course, we would find the accuracy being lower, but that's I would say like systematically could be the reason is that indeed like the geographical diversity of training data needs to be improved. Yeah.
Thanks, Hadi. Yeah, just some more questions. I think, again, scripts and codes, everything will be shared. If not in emails or in the Google Docs later on. There are some questions about the restoration. How is it, like what is the restoration? How is the restoration potential map done? And does the restoration need consider a certain level of disturbance? So this part is actually a part that is not presented in this line of work. It's actually going to come in later. So at the moment, what we are presenting is focusing on the land cover map, which is a key element of how the restoration potential later on is identified. So just to briefly discuss that a little bit, I think we can describe the plan to sort of put in the different layers of consideration prior to identifying the restoration potential map. So we are trying to identify multiple maps. So for example, maps of conservation areas against non-conservation areas, maps of previous land cover maps, as well as the most recent land cover map, which is what we are currently generating. And based on this, identify some changes that has happened in areas, and based on that, determine the restoration potential. So again, the restoration potential we'll focus on areas that has the potential of certain restoration intervention. So it's not focusing on saying that this area is degraded or this area has a specific feature in terms from biophysical perspective, but it's more on what kind of restoration options can be considered for these different areas. So yeah, that's just a little bit of description of how the restoration potential map is done. There's another question, I think a very interesting one, about the usage of disturbance mainly from selective logging and fire in the training data and features of the land cover mapping, of the automated land cover mapping algorithm. Probably you want to comment on this one, Hadi?
Well, I think I cannot answer that in a short way. But may I suggest we could like come back to these questions that we can collect now in the chat, because I'm also like concerned about the time now. It's I think it's 4 o'clock, and yeah, because there are many other sessions that I'm sure that other meetups that I'm sure the participants would like to join as well. And I think let's keep the discussion going on in the follow-up emails and communications if it's fine. Yeah.
Perfect. So we anyway are going to provide you with some emails summarizing what we're doing today, links to the presentations, links to the codes, and of course our contact information. So yeah, we can continue the discussion. It's been a great discussion, and there's a lot of super interesting questions. And hopefully we'll hear more from you, and we can maintain the network that has been built from this meetups. Okay. Thanks a lot, everyone. Thank you very much for your participation, and have a nice remaining of the day.
Yeah. Thank you, everyone. Enjoy the rest of the summit and keep in
Bye.
touch.